Hello everyone, welcome to the group meeting. Today we are very happy to have Nick telling us about decoupling identities for limited Matroids.
Oh, thanks so much. It's great to be here. It's great to share with you this work. It's been developing over the past 5 years or so between me and my collaborators, especially Freddie Cacciazzo, and starting in 2019, Alfredo Guevara and Sebastian over there. So, okay, so this is about first of all, points on a line, the space, moduli space, the so-called moduli space in M0n. These are represented by 2x-n matrices. And if you fix 3 points to be 0, 1, and infinity, and you can choose n-3 punctures to vary arbitrarily. And we assume that all 2x2 minors here are non-zero. So if we assume that these are over the reals, then this decomposes into some number of open tiles. All these tiles are simplices. And in the case that we order the coordinates, say 0 less than x1 less than x2, and so on up all the way up, that says that all of the Plücker coordinates, all the 2x2 minors, are positive. And so to motivate the title of the talk, the general structure of such decompositions with sign vectors of Plücker coordinates has been formalized into a general framework called oriented matroids. So that's kind of going to be the backdrop for the talk. Should keep that in mind that exists. Okay, so M05, the real configuration space, decomposes P2 into 12 regions. And you can see here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And among these, exactly 2 of these are bounded in this particular chart that we have chosen. That has a nice topological interpretation. Yeah, 12 tiles, and in general, the number of tiles is n-1 factorial over 2. They're all simplices, and they're related by relabelings of the columns and by Murray's transformations. Okay, so here's the roadmap for the talk. First, I'll recall the formalism due to Cacciazzo, He, and Yuan for scattering amplitudes. It's formulated on the moduli space M0n as a kind of multivariate residue. Then I'll talk about how oriented matroids formalize the notion of decoupling identities, which occur in gauge theory. You have a notion of color. In part 2, I'll switch gears to a more combinatorial and geometric flavor and talk about more recent work, building on the CHY formula and extending it in what we call generalized bi-adjoint scalar amplitudes. So these are amplitude-like objects, which are still somewhat mysterious, but we've made a lot of progress in understanding them and hope to see much more in the near future. And then we'll talk more about some combinatorial techniques and tropical geometric techniques that help us to understand these objects. Here's some notation, the kinematic space. We have the momentum conservation condition where the sum over Sij for I does not equal j equals 0. N of those conditions brings the dimension down to n-2, choose 2, especially for the mathematicians in the audience. The Grassmannian, I'll denote by G of Km, K by N matrices modulo row operations, and we'll assume that at least one maximal K by K minor is non-zero. The open subset, G circ Km, assumes that all K by K minors are non-zero. And XKM is the torus quotient of the G circ, where we mod out by scaling by on each column separately. And so we note the convergence in notation x2n equals m0n. So we'll note here that genericity does not mean that the points are just pairwise distinct in xkn. It's more interesting. It says that no k points can lie on a single hyperplane. So here I've given one particular.
Stronger than pairwise distinct, right?
Yes, stronger. Did I say? Yes, stronger. Yeah, stronger. Yes. Yes. So that means that compactifications will have a lot, substantially much more structure. So as we saw for n equals 5, m0n is tiled by 12 open cells, and there are n-1 factorial over 2 of them. So define the Park-Taylor factor, divide it to be the reciprocal of the product of all 2 by 2 minors in some cyclic order, P12, P23, P34, to Pn1. If we chose a cyclic order alpha, then it becomes that. So for example, for M05, here is how we associate. We're going to associate to the tiles. Each tile will associate a Park-Taylor factor as such. And you can see from the labeling, first, these are the 1, 2, 3, 4, 5 lines. So it's the complement to 5 lines. And here we associate 2 Park-Taylor factors, 1, 2, 3, 4, 5, and 1, 3, 2, 4, 5 to the bounded chambers, to the 2 triangles. And of course, you can do the same for the unbounded components.
So you define such a function for every cell in that complement.
Exactly. Okay, and you might call this a gauge fix, where we fix 3 of the punctures to be 0, 1, and infinity. Then I want to illustrate what I want to introduce this formula due to CHY, so-called scattering potential. And this is what it looks like in this particular chart. We have n-3 factors of xj, n-3 of 1 minus xj, and some binomial number of differences of coordinates. And as a coefficient of each logarithm, we have one so-called Mandel-Stem invariant, this AB. And this, you can see that this is well defined on the moduli space due to momentum conservation. Recall Sij, where you sum j from 1 to n equals 0. That makes this object well defined, not on just the Grassmannian, but on its torus quotient M01. So for generic Sij, there's a somewhat classic theorem of Archenko found by CHY independently that the configuration space has exactly, at least that's my understanding of the history, that the scattering potential has exactly n-3 factorial critical points. And when the Sijs are real, those critical points reside in the bounded, one in each bounded chamber or bounded tile. So here's the formula that they introduced. So given 2 cyclic orders and 2 tiles, you take the product of the 2 Park-Taylor factors, divide by the Hessian matrix, the determinant of the Hessian matrix of S, and then sum over all of the n-3 factorial critical points of S. Okay, it is what it is. It's actually a very beautiful formula in that it reproduces the usual Feynman diagram expansion as just one single object. I mean, so instead of having some number of a collection of Feynman diagrams where you replace each internal edge by a propagator, well, you have one single formula. And so a note for experts that using the global residue theorem, if you want, you can see CF Griffiths and Harris on algebraic geometry. You can rewrite this as a multivariate residue formula. Or you take the residue where the product of the 3 partial derivatives of the scattering potentials are in the denominator.
Remind me, what is S?
S is the S is the scattering potential area.
Oh.
So a quick example, I'm going to just show you how the machinery works. In case n equals 4, there's 4 minus 3 equals 1 critical point, so it's really super straightforward. Here's our scattering potential. There's the part-Taylor factor, 1 x minus 1 times x in the denominator. I should mention that usually Mendel-Stem invariants are inner products of momentum vectors, and as such they come with a dimension, and which may result in some nonlinear constraints on them. But let us calculate the m of alpha here. So if we solve for the critical points, we find exactly 1 S12 over S12 plus S23 from this critical point equation. So we're going to plug that in based on the formula, and we find the beautiful formula for the two Feynman diagrams embedded in a disk with a cyclic order fixed that fit there. So 2 cubic Feynman diagrams embedded in a disk, subject to the cyclic order 1, 2, 3, 4 on the part-Taylor factor.
So does this formula in general give us planar phi cubed amplitudes?
Yes, planar phi cubed, and it has been modified to give rise to a number of others, such as NLSM, special Galilean, Yang-Mills. Yeah, exactly. Okay, so we've looked at the CHY formula now. So 2 things that we want to do next is introduce something called minimal kinematics. That is, n minus 3 factorial is still a big number, really big number. It grows quickly, but it turns out that if you set to 0 some of your Mendel-Stem invariants, we assume that the dimension of the dimension d is quite large in this case. So that we can do that, then the number of critical points will drop, and we can actually compute it. We can compute amplitudes, restrictions of amplitudes, where some of the Mendel-Stems are set to 0 for quite large n. Behavior is a little bit different, but we can still gain a lot of insight. So the basis, first let me remark for the mathematicians, especially the poles of the phi cubed amplitude are of this form. We take a subset of indices from 1 to n, and then sum over all pairs in that subset. And as you vary over all subsets, these are exactly the poles of the phi cubed amplitude. In the case when we have for planar phi cubed, we introduce a more compact notation. If you imagine an n-gon with cyclically oriented vertices, cyclically labeled vertices, for each chord ij in the n-gon, we define a linear function, a propagator, as such. And so you can see there are n choose 2 minus n chords, and this gives you all the poles of the planar phi cubed amplitude. And moreover, they're actually, you can show that they're linearly independent, which is a quite nice feature. Yeah, so here we straightforward calculation shows that they're linearly independent. Okay, so here you want a nicer set of a nice coordinate system on M0n. You can do that by taking the scattering potential, which was defined in terms of logarithms with Mendel-Stems as coefficients. Well, if you just do a little bit of linear algebra, you can arrange this such that when you take the log, you have xij times logarithm of something. I'm writing this as a logarithm of the product, but it just expands. And the logarithm of something when you collect terms is this beautiful cross ratio. Pij, pi plus 1, j plus 1 in the denominator, pi j plus 1, pi plus 1 j in the numerator. So the question, which is solved by minimal kinematics, is it possible to simplify the computation by reducing the complexity of the scattering equations, right? They're like really nonlinear. So we'll set some of them to 0, and the number of critical points will drop. So I explored this in joint work with Freddie Cacciazzo, and then subsequently with Bernd Sturmfels and Anil Pfister. So we explored this in some detail for M0 and XKN. So minimal kinematics. We'll impose some linear constraints on the planar basis elements. Just saying that Xij is equal to the sum of new variables alpha 1 through alpha n minus 2. This introduces linear relations among the Xijs. And the effect is you set to 0 most of the Sijs. Good number, and here's what you're left with. Now recall that we said earlier that when the kinematic invariants are real, there's one critical point for each bounded top. Okay, so when you put these linear constraints on the Xijs and set to 0 the corresponding Mendel stems, you get exactly one critical point, and that critical point determines this parameterization of M0n. You can write it this way. And here you can see when the alphas are positive, every 2 by 2 minor is positive. So just a quick illustration here. How it collapses, well, planar phi cubed amplitude, when you impose these constraints, simplifies radically to the simple fraction here, suggestive of a simplex. It is a triangle in this case. Okay, so here is a quick depiction. This is sort of digging more into the combinatorial structure. Maybe let me go quickly through this slide to the next one. This is a little bit to digest. So, okay, so here we have the combinatorial formula for the planar phi cubed amplitude is sum over all triangulations of an n-gon. And you take a product of the chords in each triangulation. So we have an n-gon. And to this n-gon, we associate 1 over the product of the chords, x15, x14, x24. That's pretty straightforward. And we have to sum over all such triangulations. So it's the idea of showing that for when you impose those constraints on the Xijs, you get this simple formula. It's actually a triangulation of a beautiful polytope that is known in combinatorics in work of Gelfand, Graf, Postnikov, connection to some hypergeometric systems. So each alpha ij becomes a so-called simple root of a type AN. If each alpha, becomes a simple root, and then you can see the 5 simplices triangulating this polytope that they considered in their construction. So maybe now is a good time to sort of slow down and pause for questions. I think we're gonna shift gears in a second. Please interrupt me at any time if I'm going too fast or too slow. Yeah.
Do you have some systematics of how to set different numbers of Sijs to 0? Do you, for example, see the zeros when you set too many Sijs to 0?
Yes, and of course, you have observed this work. You're seeing these structures, zeros of planar phi cubes. So structure is that if you set certain SIJs to 0, as you've observed in these, Nima and others have observed, and what happens is that the amplitude actually factors, and you can pull out of this formula one copy of a 4-point amplitude, and then another factor. And so you see the 0 when this 4-point amplitude, when the numerator of that 4-point amplitude becomes 0. Yeah, so those are the zeros when a 4-point amplitude pops out.
But do you have some sort of different Matroidy way of seeing it?
For minimal kinematics, yes, there is something like that. It's a little bit far afield. I mean, you have to get into some two trees and such things. Yeah, there's an incredible amount of structure. Yes, there's some matrices. Okay, so finally, moduli spaces. So I just want to illustrate here what is an oriented matroid? Oriented matroids, which are encoded by sign vectors of Fluker coordinates on the Grassmannian, and if we restrict to x to n, then there are fewer. It's characterized by the 5 possible chords in a pentagon. Apologies for the labeling on the U's. This should be U24 here. U1 should be U24. That should be U35 and so on. But the point is, you can see when you have a sign pattern of all plus, all negative, not all sign patterns are admissible. But if you tabulate those which are realizable by some point in moduli space, then you get the correct number. N-1 factorial over 2. So here, switching to decoupling identities. So we're associating each tile a differential form of logarithmic singularities on its facets. Okay, and what we're going to do is we come with a cyclic order 1, 2, 3, 4. We plunk in 2, 3, 4, 5, and we plunk in the first index in all possible positions. Of course, this is well known in gauge theory as a manifestation of U1 decoupling. Mathematicians. Yeah, and so, oh, sorry. So that's the structure that this construction in oriented matroids is called a one-element extension, and there is actually a pretty rich theory here. Next, what I want to do is extend the explanation for M0n to these higher K projective, higher K moduli spaces XKN. And so now we're coming to we're coming up to date with my work with Sebastian and Alfredo and Freddie. So we're going to look for 2 things in this moduli space. X, yes.
Wait, sorry, when you say decoupling, is it only the U1 decoupling identity? Like usually we have also the relations that project down the number of independent amplitudes to n-3 factorial. Are you able to see that with your matroid picture, or is it just U1 decoupling?
No. You can also see KK. You can also
K gets you to n-2 factorial. And then how do you get to n, because all of that's just group identities.
Yeah, exactly.
You get down to n-3 factorial, since that's what actually uses non-trivial input of the amplitude.
Exactly. Yeah. So that is a deeper structure which does not really manifest itself from the oriented matroids, to my knowledge anyway.
Okay.
Okay. Good question. So yeah. So I'd like to generalize this, like go to X36, which is what we considered at the beginning in 2019. So this is 6 lines in the projective plane. And to each, this space X36 is decomposed into some number of tiles. And each tile has associated to it a differential form. Here I'm writing the coefficient of the of dx1, dx2, dx3, etc. In fact, there are exactly, unlike in the case M0n, where all simplices are related by relabeling. In this case, you get a decomposition of the tiles into 4 different permutation types. And each one of these tiles has associated to it some generalization of the CHY formula. This whole formalism together, we compute generalized bijoint scalar amplitudes. And as I said, it's an important question from our point of view to figure out what lessons are to be learned from this. But here are the 4 integrands that you see here. This is the standard Park-Taylor factor, generalizing the k equals 2 version, and you get these three other constructions here. So here are the actual line arrangements. On the top left, we have exactly an arrangement with 6 triangles, and there's exactly 1 convex hexagon in the center. Okay, so you can see, I've done this right, yes, each triangle becomes a factor in the denominator. So it says, if you want to go to the boundary of the configuration space represented by this tile, you slide one of the lines until one of the triangles shrinks to a point. And so your D-log form has to have a singularity there. And so it's pretty straightforward for the first 2 cases. When we slide one line over the triangle, we still have 6 triangles. Okay, so the constraint on forming these, I should say, is in order to have this make sense physically from the point of view of the scattering equations formula, you need there to be a homogeneous torus weight of 3 in each index. So 1 appears here, 1, 2, 3, 5, 6, 1, and 6, 1, 2, and similarly in these cases. But unlike for M0n, yeah, as I said, the number of boundaries, or the number of triangles will increase, the number of permutation types increases. And so we can have anything from 6 to 7 to 10 triangles in the arrangement. And in this case, some of the triangles wrap around infinity. So you won't see them in the as bounded things in this configuration. Okay, so just a quick word about on the math side. There's if you want to sort of make systematic and this construction to axiomatize it using oriented matroids, then there's a theorem due to Bone and Dress, which says that we can interpret our line arrangements in P2 as certain rhombus tilings of a zonotope. So in that case, this is the standard Park-Taylor factor, where where you see triangular regions for 1, 2, 3, 2, 3, 4, 3, 4, 5. And you can sort of mutate by flipping triangles. So we are 1, 2, 3. You take this subdivision of a hexagon and you flip it to the you do this move and you flip it here. You get the other type 1 guy and then you flip it again. You flip 3, 4, 5, and you get the type 2. So the type 2 with the 7 factors in the denominator. So the point of this is I just want to say that there's a very substantial theory here to oriented matroids, and it's been very useful in our study of forms on XKN spaces and generalized amplitudes. So, okay, so back to decoupling identities, the subject for the talk. We're going to fix an arrangement of n-1 projective lines. Projective copies of P1 embedded in P2. We're going to take a new generic line in all possible ways, sort of slide it around to introduce a sixth generic line. On X36, turns out you get 31 possible arrangements. So by the analogy with the X2n story, this should give rise to some irreducible, some decoupling identities, as decoupling-like identities as well. So in this case, not all of the identities are irreducible, right? So you take a U1 decoupling and you have n-1 sum-ends. There is no sub-identity among those sum-ends. In this case, the set of 31 guys that you see there satisfies some sub-identities. But we developed algorithms to get the irreducible decoupling identities, and here is one of them. So you have like there's a decoupling identity with 7 terms, 8 terms, and maybe 15 terms. It depends. And this is supposed to be analogous to the decoupling identity among the part-Taylor factors shown at the bottom. Okay, so maybe pause for a second. Any questions? Okay, part 2. Part 2, moving to, so far we've had the scattering equations, we've had to solve them for, solving them for M0n or X2n is already difficult. But it turns out if you want to solve them for some XKN, X36 even, it's much more complicated. So we need a sort of combinatorial, some sort of more powerful machinery to understand these rational functions, these amplitude-like objects. Okay, so that's what I'd like to explain now. So the one observation is, let's start from scratch again. Go back to M0n and the CHY formalism. Okay, so we have this notion of Grassmannian duality between GK comma n and Gn minus k comma n. That says that you should have like a dual copy of phi cubed amplitudes formulated on the dual Grassmannian modulo torus. So what we like to say is that CHY sort of missed the opportunity to ask what comes between these two copies. And what comes between is the formula with Sebastian and Alfredo that we exploit. So we generalize the CHY integral to xkn, is filled in the gap. And this now, hence comes the connection to the math literature. There's a very exotic object in math called the tropical Grassmannian, and in particular, a certain positive part of it. Once we had seen that, then we could dig through the math literature and really gain a lot of information into these amplitudes. Okay, so quickly we can define a scattering potential S again in the obvious sort of natural way. Take the logarithm of the 3×3 minors, multiply it by some new parameters, S, A, B, C. These are not related to usual Mandelstam invariants. Not a sum SAB plus SBC plus SAC. So it's a completely new parameter. This is well defined on X3n due to a set of n linear relations among the Mandelstam invariants which you impose. Here P is a maximal minor of what you may choose to be this projective frame. as such. And so you see that X36, the first 6 columns has a dimension 4. So as I said, they're linear functions on the space of they're symmetric tensors. And they satisfy this generalized notion of momentum conservation. For each t, you get an identity. For each t equals 1 to n, you get an identity among them. And that's equivalent to saying that S is well defined on the configuration space. So for each pair of these part-Taylor factors, these products of the cyclic minors, one reciprocal of their cyclic minors, for each cyclic orders alpha and beta, well, you can define it in the analogous way. Take the product of part-Taylor factors, divide by the determinant of the Hessian matrix, and sum over all the critical points. Yes.
I don't understand what's being said. You call these generalized biadjoint scalar amplitudes. Is there a theory which has these amplitudes? Or
That's
a mathematical thing we're discussing.
It's a mathematical construction, yes. Yeah. We have some notion of color of a formulation of color. We have some notion of that, some interpretation of decoupling identities, but yeah, it's a purely mathematical theory. So I want to show you what this looks like first for 6 points at k equals 3. What are the new features? Well, for usual phi cubed amplitude, you have the property, you have this pairwise polar compatibility. A refinement diagram that results in the fact that every Feynman diagram associates to the amplitude n-3 propagators. The novel feature for k equals 3 is that now you may have some more than the expected number. Here you will have the same number as the dimension of the configuration space, 4, but you may also have 5 factors in the denominator. Now they are not linearly independent. Okay, you still can take no more than 4 residues, but you have these interesting numerators and interesting linear relations among the poles, such as this. So these new poles R1, 2, 3, 4, 5, 6 enjoy some cyclic symmetry. They're actually invariant under permuting 1, 2, 3, 4, 5, 6 to 3, 4, 5, 6, 1, 2. So that means that this whole object here, the whole second object, is actually permutation invariant under permuting the blocks 1, 2, 3, 4, and 5, 6. Okay. So this is actually closely related to the snowflake Feynman diagram that you see for the 6.5 cubed amplitude. Okay, so it turns out that you might guess, as we did, that the only integrand that you need is the part-Taylor factor, the k equals 3 part-Taylor factor. That is not true, and you can see this because you have this sort of non-planar Feynman diagram, Feynman-like diagram. You have 1, 2, 3, 3, 4, 5, 5, 6, 1, clearly consecutive, but then you have this 2, 4, 6 popping out. Okay, so that's a feature, and that suggests the need for the new integrands beyond the part-Taylor factor. That suggests the need for investigation into oriented matroids in particular. Okay, so here is so to investigate this, the planar part, you want to generalize the planar basis. Not so obvious how to do it. Remember, we have the planar basis of chords of the n-gon. And we'd like to generalize that to some x sub a k tuple maybe not so obvious how to do it. But there is a way to do it. So is there something similar for the planar basis elements? Is there a similar construction? Is there an analog to this pairwise compatibility notion, which says that, for example, it says that the two chords x1, 3, which is S2, 3, and x2, 4 equals S1, 2. These are not compatible and they do not appear together in a Feynman diagram. So we'd like a notion of that for these new objects. Yeah.
You have constraints on your S's, which in the usual case often be written in terms of momentum vectors. What's the analog of that for your S's?
Yeah, for that. So the spinor helicity formula in terms of formalism, writing momentum vectors as 2 by 2 rank 1 matrices. That has a generalization if you replace 2 by 2 matrices, rank 1 matrices with rank 1 3 by 3 matrices. Define then Sijk is the determinant of the sum of 3 of these. So Sijk in the new setting equals determinant Ki plus Kj plus K little k, where each of these is a rank 1 3 by 3 matrix. Then momentum conservation, the analog of that is that K1 plus Kn. This has to be a rank equals K minus 2. So, I mean, when K equals 2, this says it's rank 0, so it is the sum is 0. Yeah, so you have, yeah, so this has some nice properties. Yeah. So that's how we found the analog of the sort of more close to a physical realization of the Mandelstam invariance.
It's not that close because I don't understand what to do with how to interpret this rank 1 3 by 3 matrix.
It's not that close, but it's on the way in. One step. Okay, so this is a little bit of combinatorics. For my physicist friends, you can sort of close your eyes to this side, but it is beautiful, and it is necessary in order to get linear independence for this new planar basis elements. So we need a notion of a new polytope, which you encounter a lot in geometric combinatorics, so-called hypersimplex. Hypersimplex is the convex hull of all k-fold sums of basis vectors as you range over all k-element subsets. Okay, this so in the case k equals 2, n equals 4 and k equals 2, delta 1 4 is a tetrahedron. Delta 3 4 is another tetrahedron. And delta 2 4 is an octahedron embedded in the hyperplane in R4. Okay, so first, so here is the sort of formula. We define a distance function. So this is defining x24. We're going to define the coefficients of the Mandelstam invariance in this linear combination, such that modulo momentum conservation, it reduces to a planar kinematic invariant. So we go down to this bottom vertex of the octahedron, and we take steps upward. 0 to 1, so this is the vertex E2 plus E4, up to E2 plus E3, that's one step. And you take another step to the vertex E3 plus E4. Take another step up here to the vertex, E1 plus E3, and so on. Okay, so if you do this, and then you take this sort of directed distance function and divide by the number of particles, n, which in this case 4, and that reduces to a planar kinematic invariant, one S12. Yeah, so in general, I believe I have the formula in the next slide. In general, the prescription is the following. For any two vertices of the hypersimplex, for any vertex of the hypersimplex, we're going to define a planar kinematic invariant, like Xij. And so what we do is we fix the vertex E sub I, and then we take our walk in the directions E1 minus E2, E2 minus E3, etc., in the direction finally En minus E1. And we calculate, we vary over all walks and find the minimum length until we get to the coefficient we're after. Okay, so if we do this, so Xj, this new analog of the planar kinematic invariant, is a linear function given by this, where the directed distance function is the coefficient of the Mendel-Stem invariant SSI. So as in the case k equals 2, they're linearly independent. And the magic happened, that's magic. I mean, proving that they are linearly independent is pretty non-trivial unless you had this distance function. I mean, you could define it in other ways, but having this distance function proves linear independence, proves a basis. And moreover, if you choose any vertex of the hypersimplex, like E1 plus E2 plus E3, in delta 3n, well, this is a cyclic interval. It's a funny rule, but the indices make up a cyclic interval, which says that Mendel-Stem invariant X1, 2, 3 is actually 0. It's 0 modulo the usual momentum conservation relations. So it's a little bit weird, but it's kind of powerful actually. So on the combinatoric side, well, you really want to be able to do something with these planar kinematic invariants. And for that, you have to characterize the identities which they satisfy. They satisfy identities called tropical Pluker relations. These characterize a certain polyhedral fan. These characterize a polyhedral fan in which consisting of a collection of polyhedral cones that are glued together in some way, such that the intersection of any two cones is another cone in the fan. Okay, so these relations, which are satisfied by the directed distance functions, which are satisfied by planar kinematic invariants, these encode an object called the positive tropical Grassmannian. And the combinatorial, what's really important here is that the way these cones fit together, the structure of the cones, the structure of the fan, completely dictates the function you get from evaluating the generalized scattering equation, this generalization of the CHY integral. Right, so this combinatorics is really necessary if you want to understand how to generalize the CHY formula beyond M0n to XKM. So here is what the M5, the partial amplitude with a cyclic order 1, 2, 3, 4, 5, what that looks like. So you can see actually the literal polyhedral fan, which I wrote here, consists of these 5 cones And in the middle of each cone, you get a usual Feynman diagram in the middle of each cone, and they're glued together in a nice way. On the other hand, remember this is k equals 2, so this S1, 2, 3 is now a sum of Sij's. So if you want to extend to the full phi cubed amplitude, then you have this picture on the right. You have 10 Mendel-Stem invariants, and they are connected by an edge exactly when the two factors, the two Sij's appear in the same Feynman diagram. So like, if you want to see the planar phi cubed amplitude, S12 and S34 appear together because they're connected by this edge, and they appear on the boundary here. And so like, for any cycle in this, you get a copy of the planar phi cubed up to the permutation. Quickly, so I want to show, again, this is just, they look like momentum conservation. What the important part is the bottom here. Momentum conservation is actually equivalent to asking that each x sub ij, when I and j are cyclically adjacent, that each one of those evaluates to 0. So that's equivalent to the notion of momentum conservation. Maybe let me pause again quickly. Maybe that was a lot to digest so far, so there, questions or comments? Okay, now the notion of compatibility. It's very simple, actually. Remember here we had notion of compatibility is just that when you write Sij and SKL, the two guys cannot cross in an n-gon. Well, that generalizes to the requirement that you take the sum of indicator vectors, take the sum E1 plus E3 minus E2 plus E4. We're checking whether X13, X24 are compatible. Well, this is equal to E1 minus E2 plus E3 minus E4, which is 1, -1, 1, -1, which alternates sign a bunch of times, 4 times. Okay, a little bit technical, but turns out that's exactly what's needed for the generalization. So xi and xj can appear in the same generalized Feynman diagram if and only if E sub I minus E sub j alternates sign exactly twice. So it's pretty simple, actually. Is that questions about this? So for the planar phi cubed amplitude, Feynman diagrams are in bijection with triangulations of an n-gon. And triangulations of an n-gon have a nice enumeration in terms of the Catalan numbers. Two, 5, 14, 42, 1, 32. Well, you'd like to enumerate the number of maximal collections of compatible planar kinematic invariants. So you can do that. And on the boundaries of that triangle, you get the Catalan numbers. 2, 5, 14, etc., 2, 5, 14, etc. But you can see here how they kind of blow up. Now, the reason I'm showing this is maybe for mathematicians in the audience and physicists who are interested in cluster algebras, these are related to the number of Plücker clusters for the Grassmannian cluster algebra. So there's some sort of connection between generalized Feynman diagrams for generalized bigenome scalar amplitudes on the one hand, and cluster algebras for the Grassmannian on the other. So cluster algebras appear in n equals 4 super Yang-Mills, So, anyway, lots of connections here. So back, just want to return to the amplitude real quick. We had like before, it was, yeah,
Wait, sorry, for the connection to the graph, sorry, GRKN clusters are infinite beyond, for sufficient K and sufficient N.
yes.
So how are you writing down finite numbers there for saying that there are a finite number of clusters?
Only those clusters which are consist of only proof coordinates.
Oh, okay, I see.
Yeah. So our objects are very much not infinite. One could extend them by including non-Kluger cluster variables, but we're not doing that because that would sort of screw up the configuration space. Anyway,
Sorry, just one clarification. Do you mean, are you isolating to clusters that have at least one Plucker coordinate or clusters where all of them are Plucker?
all of them. So on a planar basis, then this linear dependence among the poles is completely manifest. And so, well, if you kind of stare at this, you can check by hand that every difference of like E1 plus E2 plus E5 minus E1 plus minus E3 minus E4, that alternates sign exactly twice in every case. Of course, it's not sufficient when you have this linear combination. That's another interesting layer of complexity. But it suffices when you have only monomials in X. M37, M38, it gets very interesting very quickly. So M37 has, the planar guy has 42 poles, 693 generalized Feynman diagrams. So these are the two ones that are not single monomials in the X's. M38 has 120 poles, 13,612 generalized Feynman diagrams, and so on. So you get the idea. It sort of explodes in complexity. Okay, now for the summary and future work. So we considered the problem of enumerating critical points of the scattering potential. One can use minimal kinematics to sort of peek into the structure of scattering amplitudes using the CHY or CGM formalism. And we saw that when, in the case of the planar phi cubed amplitude, M to N, when you reduce to minimal kinematics, equals alpha 1 plus alpha n minus 2 divided by the product. Well, that's just like an extreme situation. I mean, we're setting to 0 sort of the maximal collection of Mandel-Stem invariants, such that the amplitude is non-zero, but you can set things in between, such that the phi cubed amplitude simplifies in some ways, and you gain some new behaviors, and insight into some new behaviors. And yeah, and so you can hopefully, and I think this was done in the work of, in some work recently by Nima and collaborators, Nima and Carolina, looking into Yang-Mills amplitudes in this way and NLSM. Anyway, so the question is, are there broader applications for other amplitudes? Second, decoupling identities seen through the lens of configuration spaces. So we developed that for X36, X3N in particular. There's a way to get irreducible decoupling identities. Because in general, if you take n minus 1 hyperplanes and shove in an nth guy, the corresponding forms are going to satisfy a bunch of irreducible identities, a bunch of sub-identities. So there's a way to do that. In the theory of oriented matroids, these are called one-element extensions. There's a rich theory behind that too. Some progress on the Lie theoretic realization of color factors. More investigation is needed. It seems to be very interesting as well. And finally, the most important question from my point of view, what, if any, physical lessons are there to be learned from these new objects? Thanks a lot.
Is the generalization for color factors like a like a three algebra, like a Lie 3 algebra or something, or is it something more exotic?
No, that's what we thought at first. Yeah, that's what we thought at first. To produce the decoupling identities, what turns out happening is that you fix. Say we have 6 lines intersecting like that or so. So what we needed to construct the irreducible decoupling identities, you basically take a standard U1 decoupling identity on either of the 2 projective lines, right? So you get this maps X36 onto M05 cross M05. We have 2 copies of M05, one on each line. So the analog of decoupling identities, which I found so far anyway, which produces irreducible decoupling identities, extends directly from decoupling identities for usual amplitudes. Just extend it, you uplift it from M0 comma N minus 1 into X3N. So yeah, I mean, as far as 3 algebras, yeah, that's what we thought at first, but yeah, that didn't seem to be the right framework. Maybe some more exotic object. Yeah.
Any question?